inviting me here to share our recent result about the transaction fee mechanism for blockchain. And this is a joint work with my advisor, Elaine. So what is the transaction fee mechanism on blockchain? So blockchain is a distributed ledger, and there are a lot of transactions on each block. And on blockchain, there are two kinds of players, users and miners. So users that have transactions that they want their transactions to be put in the block. And miners' job is to maintain the blockchain by putting those transactions into the block. And the transaction fee is miners' reward. Okay, so let's say our amazing PC chairs are the users. Each of them has the transactions that they want to be included in the block. However, let's say the block is super small. It can only contain 3 transactions in the block. In this scenario, what should we do? So this is really similar to the case that if you only have a few items, but there is a lot of buyers. In this case, we can run an auction. So in terms of blockchains, let's say K is the block size. That is, only K transactions can be included in one block. Then this is like an auction where we sell K identical items. And in this case, each transaction is associated with a bid. And the fee mechanism is going to decide which users are confirmed and how much should they pay. So this is transaction fee mechanism. Okay, so what's the problem of the current mechanism? So take the Bitcoin as an example. Bitcoin uses the pay your bid or the first price auctions. So it works as follows. The miner just picks the top K bids into the block, and all of them are confirmed. All the confirmed user pays their bids. All the payment goes to the miner. That's it. So what's the problem? It encourages user to bid untruthfully. So let's say, if my true value is $2, am I going to bid $2? Not necessary. I'm going to monitor the markets, and I just try to bid the bare minimum that I can get into the block. So for user, this is annoying because I need to monitor the network, and I also need to guess what should I bid. If I bid too high, I will regret. So this is bad for the user experience. Can we solve this problem? Yes. We can use the second price auctions. So in terms of blockchains, that the top K transactions are confirmed, but all of them just need to pay the K plus 1 price. And from the traditional auction theory, it tells us that second price auctions, user is always, the best strategy for user is always to bid truthfully. However, blockchain itself is a decentralized system. So that means no one is trusted. Miner itself is also an active strategic player. And second price auction is easily to be manipulated by miners. So for example, miner can just inject the bids, maybe 5, and in this case, everyone will pay more. And moreover, miner can also collude with the user with the lowest price. For example, miner can tell the user not to bid $3, please bid $5, and we can split the profit under the table. And what's worse is that on blockchains, we have smart contracts. So it's really easy for miner and user to form a coalition that they can split the profit according to the state of the blockchain. So according to the discussion above, we can conclude 3 desired properties that we want. The first one is called UIC. That means user's best strategy is always to bid truthfully. In this case, user doesn't need to monitor the network. It's easy to use. The second property is called MIC. That means miners should not have incentive to manipulate the system. The third one is called side-contract proofness, which is parameterized by a number C. That means even if a miner colludes with C users, their joint utility should not increase if they deviate from the protocol. And again, because blockchain is a decentralized system, so miner itself is also a strategic player. So unlike the traditional mechanism design that maybe we can trust the auctioneer or the government, here no one can be trusted. So how to resist the minor deviations is a new challenge in the blockchain context. And actually, there are already several earlier works that try to analyze and propose different kinds of blockchains, different kinds of fee mechanisms, but all of them fail to satisfy all three properties at the same time. And actually, in the EC last year, Team Rough Garden asked a question that, can we have a dream mechanism that satisfies all three properties? This is the question that we are going to answer today. So let's check what is the state of the art. So actually, Ethereum already does a great job. So in last year, Ethereum officially deployed the new fee mechanism called EIP'22. We won't talk about the details today. I'm just claiming some facts. So this is what EIP'22 achieved. So when the network is uncongested, that means the demand is lower than the supply. Then the mechanism just acts like the posted price auction. So here, there is a predetermined price, R. Everything higher than R is confirmed and just pay R. And in this case, we are fine. However, if the network is congested, that means the demand is larger than the supply. Then the EIP'22 will reduce to the first price auctions, which we have seen is not UIC. Users are not encouraged to bid truthfully. And here, what is interesting is even if the network is uncongested, even if EIP'22 works as a posted price auction, by design, miner actually gets nothing. All the payment is burned, totally eliminated from the circulation. So why does EIP'22 choose this design? And again, go back to our core questions. Can we have a dream mechanism? Unfortunately, no. So in our paper, we show that if the block size is finite, that means the number of items you are going to sell is finite. No non-trivial mechanism can satisfy UIC and 1 as a CP at the same time. Here, by non-trivial mechanism, my point is the only mechanism that satisfies both properties is always to reject anyone. But that makes the blockchain useless. And another remark is 1 as a CP means the miner collude with one user, which is the weakest coalition we can conceive. So our impossibility says that if you want your mechanism to encourage the user to always bid truthfully, it is even impossible to resist the weakest coalition we can conceive. And to show this impossibility, we prove the following key lemma first, which is interest on its own. So this key lemma says that no matter the block size is infinite or finite, as long as the mechanism is UIC and 1 as CP, miner revenue must be 0. So that means burning is necessary. So the design of EIP'22 on Ethereum is a must if you want UIC and 1 as CP. Okay, so we have seen two impossibility results, but don't be so sad. So in this paper, we also give a positive result. So how do we bypass the two theorems I just shown? The point is that maybe the adversary we consider is too strong. So in the impossibility proof, we assume that the coalition can overbid for free. So what does that mean? So let's use the second price auction as an example. So the miner can collude with the user with the lowest price and ask the user, please bid $5, not to bid $3. And that user say, sure. Because no matter I bid 3 or I bid 5, I'm still unconfirmed. My utility is still 0. So it doesn't matter that I bid 5 or I bid 3. This makes sense if we just consider a single shot auction. However, on blockchain, there's always another block after this block. So actually on blockchains, we are actually consider repeated auctions. So if I'm the user with a true value of $3 and I actually bid 5, I'm unconfirmed now, maybe my transaction will be confirmed in the future and I actually need to pay $5. But my true value is only $3. So in that case, I will lose $2. So this is the potential cost for the adversary if they want to overbid. So we call this assumption the pessimistic assumptions. So that means if the coalition overbid and that bid is unconfirmed, that means it may be confirmed in the future, then the cost for this overbidding is the bid minus the true value. And because if miner injects a fake bid, the fake bid itself has no intrinsic value, so the cost for the miner to inject the fake bid is the exact bid itself. So this is the utility function. We consider the cost if they overbid, but the bid itself is unconfirmed. So if we consider extra cost for the adversary, this is the weaker adversary. If the adversary is weaker, it's actually easier for us to design a mechanism. So this is the result, the burning second price auctions. So in this auction, there are two parameters. K is the block size, that how many transactions you can put into the block. T is the number of transactions that are confirmed. So potentially, T can be smaller than K. So that means not all the transactions in the block are confirmed. You can conceive that we are trying to sell K items, but it turns out there's only T winners. I didn't sell all the items. Okay, so let's use this example. K is 6, T is 3. So in this case, the top 3 bids are confirmed. And all of them just need to pay the fourth price, which is $5 in this case. And miner is paid the sum of 4th to the 6th price. In this case, it's 5 plus 4 plus 3, which is $12. We show that the affirmation auctions actually satisfy UIC, MIC, and 1SCP. So that satisfies all 3 properties. This is the dream mechanism we want. But of course, this is in the weak version, if we only consider the weaker adversary. And finally, let me briefly mention what is more in our paper. So in the pessimistic assumption I just made, we assume that the extra cost for the adversary is the difference between the bid and the true values. So here we have a parameter gamma. 1 means if you consider the full difference. 0 means there is no difference. And actually, you can consider any ratio between 0 and 1. For example, 0.5 means the adversary can only need to pay the 50% of the extra cost. And the mechanism I just showed is only 1 SCP. That means you can only against single miner, single user coalition, but you can actually against a larger coalition. However, there is a price. So we also shows that for any seed larger than 1, the mechanism must be randomized. And finally, we also showed that K larger than T, that means there are some unconfirmed transactions that is in the block. That seems like, oh, we waste some space in the blockchain. That sounds not good. We also show that this is also necessary. Okay, so let me quickly mention the future directions. So our paper give a first example that maybe we can consider other relaxed model to bypass the impossibility. So it's interesting to consider maybe we can bypass the impossibility by other models. And the second one is that when I designed the mechanism, I found that the transaction fee mechanism is really interesting because it lies in the intersections between cryptography and the game theory. So maybe we can use some crypto techniques to help us to design. And this is my talk. Thank you so much.
Excellent, wonderful. So you guys are all perfect in time. So we do have time for a few questions. I already see the first one. Can you maybe move to one of the microphones? Or?
Yeah, so you mentioned when market is congested, the EIP 1559 is different. So my question is, when it's congested, how does your property satisfy?
How does my property satisfy?
Yeah, so when the EIP 1559, when the blockchain is actually congested,
Yes.
Can all the 3 properties still hold?
Do you mean our new mechanism or the impossibility result?
Both.
Okay, so the impossibility result says that, okay, so you can conceive, congested means like the block size is finite. So our impossibility says that it's impossible to achieve all 3 properties. So this is why Ethereum fails. Yes, and in our mechanism, the block size is finite. So in that example, K is just 6, and it still satisfies all 3 properties.
Okay, sounds cool.
Hi. I am actually doing research in very close relation to your topic. So I have 2 technical questions. The first one is that it seems that your mechanism only considers the collusion between miners and the users. But actually in the mining of the cryptocurrency, there are many existing so-called mining pools. So that I think that the collusion between only miners may also be something that needs to be considered to make the system robust. And do you think that your mechanism can prevent the collusion between users, or how do you think it should be modified to satisfy this property? This is my first question. The second question is that I looked deeply into your proof for the impossibility results. And I think that maybe there should be a little modification into your claim. Because when there can be infinite size, then the 1SP and the UIC implies 0 miner revenue. It needn't to be modified. But I think that the proof for the finite size doesn't have a non-trivial mechanism. It needs 2 additional conditions. One is that an infinite size of the number of bidders should be allowed, because your proof needs to inject an arbitrary large number of fake bidders. So that in actual blockchain, as the network capacity is large, but it is always finite. If we only allow a finite size of bidders, maybe this impossibility can be circumvented. And the second is that your construction also needs the miner to ignore some of the bits. So, so that I feel that an additional condition of MIC should be added. I don't know that only finite block size, 1 SCP, and UIC can prove this property. But I feel that your proof needs to add these two conditions. And about your future direction, I also did some research, and in my research, I got a result that when we don't use the gamma strict utility, but relax the UDSIC to UBNIC, then the positive miner revenue is possible. Okay. So.
Thank you very much. That was a somewhat longer question. I'm not sure if you can answer all of that right now. Maybe if you can have a very brief response, and we take the Q&A then offline. Right?
Yeah, sure. Yeah, so if I understand correctly, so the first question is about the miner-miner coalition.
The collusion between users.
Oh, user-user coalitions. Oh yes, so indeed, in this work, we didn't consider the user-user coalitions. I can quickly mention this that if I remember correctly, is that Jason Hartline's paper? Maybe I remember it wrongly. So someone already shows that if you want to against two user-user coalition, then the only feasible mechanism is post-depressed auction.
And also the collusion between miners are also not considered.
Miner-miner coalition we consider. So in this paper, we assume there is no consensus level attack. So that means a blockchain itself, consensus level is perfect. So there is like one block, no forking. In this case, you can consider even the miner is a 100% miner. You control 100% of mining power. You can, because there is only one miner of the winning block. So that miner is actually like the monopolist. So you can consider even the miner control 100% of miner, we still have all the result in our paper.
Very, very good. Thank you.
Okay.